So today we're just going to continue on as many exercises as we wanted to do. I had already put on two other exercises here of computing a loan amortization table, but I'm doing that right now in the main section. So if we wanted to skip that one and you wanted to watch those videos instead, or write a program that, given an integer, calculates the number of primes between 2 and n. Or I've got an entire book full of them here, and we can do other things depending on your interests. For example, we can do something more sciencey, the radioactive decay of radioactive elements. What else do I have here? We could do some we could do some calculus stuff. We could do, there's the arithmetic geometric mean that we already did. A lot of it is going to be math, and that's because the fundamentals are math, right? And then we could do graphical stuff. Computing pi. Where was the other one that I was thinking about doing? There should be like an EDSAC method in here. That one's kind of cool to do. If you've ever wondered how you could do the square root, how is the square root of x computed? Well, there's this series, much like the arithmetic geometric mean, that converges, but you have to have it under certain conditions, but you can get those certain conditions. So what are we wanting to see? Okay, a Taylor series. All right. There's pi. The sine function. Right? There's the sine function that can be computed using the following series. There's arctangent, et cetera, et cetera. Right? Let's just go ahead and keep it simple with sine. That wasn't in your lab, was it? I think I purged those from labs because generally people don't like math stuff, but this is the honor section, right? We all love math here, right? No? All right, well, in any case, we'll go ahead and do it this way. Now, here the Taylor series is a summation. It's a series, an infinite series running from I equals 0 up to infinite, right? And it converges, so it goes on forever. A computer can't go on forever, right? So one thing that we could do is we could take in n, where n is an approximation. We'll do this not an infinite number of times, but we'll do it n times, right? And so we'll run this from running from 0 up to n instead of infinity, okay? And here's the simple, we'll come back to it because we're going to have to reference it, but here's the simple ratio of this thing, and then we've got a power here, et cetera, right? So do we want to do this in C or Java? C? All right. So let's go over here, and let's go ahead and go. I'm just going to do this in a demo program here. Okay. All right, so I'm just going to go ahead and set this up. We're not going to read in command line arguments. You know how to do that already. Instead, what I'll do is I'll hard code values here. So suppose that we want to go for 5 iterations. Actually, 5 plus 1, because if we're going from 0 up to n, you count 0, right? And so that's the number of iterations, n. Now, that's not a great variable name, right? I mean, you could write number of iterations. That's more descriptive, but in the context, n is probably okay, right? Because we're doing something mathy. What does this sign represent? Well, it just represents sign, right? It's abstract to begin with, right? All right, I'm going to run a summation here. And if I'm going to run a summation, that means that I need to have something to put that summation in. And so let me go ahead and create another variable here. And I'll make it into a double because it is going to be fractional. Sum, right? Okay. What should I start it out as, by the way? 0, right? That's not a trick question, right? It's just, if you're going to add stuff up, then don't start it at 10 because 10 plus x, you're off by 10 already. Right? What else do I want? Obviously, I'm going to have an x here, right? So let's go ahead and create a variable here, x. Right? And I don't know, a sine of, this is probably in radians, I think. Don't quote me on that. But go ahead and give me a value of x here that we know the value of sine. Nobody has that memorized? Say what? What is the sine of pi?
0.
Yeah, okay. So do we get 0 out of this, right? Right, because if I just said, well, what's the sine of 2 radians? Does anybody know that off the top of their head? No. What's the sine of 0?
1.
Good, right? So that's another one, right? So our expectation here is that we're going to get 0 out of this thing. Do we get 0 out of this thing? So I want a loop, right? And I'm going to run it from 0 up to n. What kind of loop control structure does that say to you? A for loop, right? So for int I, in fact, I'm using the variable I in the summation already, right? If we put this off to the side here, I don't have a lot of real estate, but I can go ahead and squish this down a little bit. Nope, nope, nope. There, come on. Pixels, there we go. All right, so just to keep it over there. I is equal to, I'm going to start out at 0. I is less than or equal to n because I'm going to go up to and include that last iteration there. And then I plus plus. Okay? Now my sum is simply going to be whatever I've done so far, sum plus equals, right? That's the shorthand there. And then I just have to transcribe this formula right here. -1 raised to the power I, right? Divided by 2i plus 1 factorial, right? If you've never seen that before, that's factorial. So 5 factorial would be 5 times 4 times 3 times 2 times 1, right? And then times x raised to the power 2i plus 1. Obviously, this is all wrong, right? So first of all, let's go ahead and start. Let's fix stuff first. All right. So what should I do? The numerator here, the denominator is fine, but what do I need to do to that entire expression? Put it into parentheses. Right. Now, -1 raised to the I. Think about what happens here. I is going to be 0 at first, and so -1 raised to 0 is going to be 1. Then it's going to be 1. -1 raised to 1 is going to be -1. Right? So in other words, it's oscillating between plus and minus, and that's what you see over here. It's plus x, and then minus, then plus, then minus, then x. It's an alternating series is what those are called, right? Because it goes back and forth. So do I really need to use, say, math or POW math here to raise it to the level I? That seems like kind of a waste or an inefficient way of doing it, because it's always ever going to be 0 or positive, or it's either going to be 1 or -1, 1 or -1, and it's going to oscillate. Right? It's going to alternate. So let me go ahead and create another variable to do that for me. Sine. Right? Now initially it's going to be what? Because let's see, I is 0, so it's going to be +1. Right? And I'm going to change this entire thing to just sine. Right? And then to make sure that I'm setting myself up for the next iteration, I'm going to say sine is equal to sine times -1. I'm just going to flip the sign, right? Flip it back and forth. Is there a more compact way of writing that? Times equals -1. There, oops, times equals. There we go. All right, great. All right, what about this thing down here? First of all, can I write 2i? No. 2 times I. Okay, that's good. Factorial. Is there a factorial function for me? Well, you can go ahead and open up the rubber duck debugger and ask them. Let's bring this up. Does the math library have a factorial function? Cinema does not have a built-in factorial function. All right. Well, just like Christmas, eventually you get old enough that nobody buys you presents anymore. So our library is not giving us presents anymore. So what do? We have to give ourselves presents, right? That if you really want that, I don't know. What's the last thing I bought? Can't remember. But if you really want that present, right, then you're going to have to give it to yourself. Now here is a preview of what we're eventually going to do. We're going to have to create a function for it. And so this is going to be an int factorial function that takes int n and returns an integer n here. So this is what's called a prototype or a signature. The name of the function is going to be called factorial. It takes as input n, and then it returns a value here, of the factorial, right? Returns, and we're going to document it. Returns the factorial, that is n factorial, of the given value, n. Right? There's my documentation. Now this is called a prototype. This is something unique to C, where you have to declare, just like all variables, you have to declare them before you use them. You have to declare a function before you can use the function. So that's why I put it at the top. But I didn't actually define it, right? There's a semicolon here which ends it immediately. So what we're going to do is we're going to come down to the end, and that's where we're going to define it. Right? So assuming that we have this, we'll come back and do this later. Assuming that we have this, there's my factorial function. Right? And like any good programmer, what should I do? To implement this sometime when you feel like it. And we're going to feel like it here in a second here. But otherwise, you always leave yourselves to-dos. The reason that you do that is in certain IDEs, for example, Java over here, right? What can you do? Well, it's already highlighting it in this special blue bold text. That's because you can go down here, and it's not showing right now, but I will show view tasks. There we go. Show view tasks. There we go. Come on, you should know about this. Oh, I didn't save it, that's why. There we go. You see what happened down there? My taskbar. That anytime you have a to-do and a comment, it's going. The IDE is going to find it, and it's going to put it in this this view down here, this task view of, and it's going to be immediately. Oh, I need to do that thing. Double click on it, and it takes you there. Right? So it's a really nice pattern to follow because IDEs support that kind of stuff. All right, we'll eventually do that though. Right? All right, so POW is how I do this. And then it's not 2i plus 1, it is 2i, or 2 times I plus 1. And then make sure that your parentheses are balanced. I see some redundancies here. 2i plus 1, 2i plus 1. First of all, I should have consistent spacing. If you want to have really consistent spacing, you should do that as well. Right? And so what I could, I'm doing that twice. What I could do is I could put that into a variable so I'm not doing it twice. Right? And everybody tries to do that kind of pre-optimization. Right? But here's a non-trivial fact. Your compiler will do that for you. Right? If the compiler sees that's an expression, they're the exact same expression, and they could not have changed between them, we're only going to do, when I compile this, I'm going to actually only compile it into code that does it once and then uses it in 2 places. So, no, there's no need to pre-optimize this. You can let the compiler do it for you. Right? It's not going to be any faster. It's not going to be any more compact. All right. Now we have to do this. Right? So given n, what I want to do is I want to say n times n minus 1 times n minus 2. This is how it's usually written in mathematics, times ... times 2 times 1. So writing that out, what I'm going to do is I'm going to create another function here. For int I equals 0, I is less than n, I plus plus. I want to keep a product, int product. All right, so where should I start that product, and is this idiomatic for loop actually appropriate? All right, so I is running from 0 up to n minus 1. Is that what my summation is doing here? Nope. So how could we do this instead? If I wanted to run right to left, I would start at 1, and I would go up to and include n. I'm going left to right here. All right, and then in that, I'm going to say product is equal to product times I. Okay? All that's doing is going to 1 times 2 times 3 times 4 times 5, all the way up to n. Right? Is there a more compact way of writing that as well? Times equals I. There we go. And I can get rid of that now. Where do I start my product? If it's like a sum, I would start it at 0. But how does multiplication work? It's always going to be 0. So where should I start it instead? 1. Okay. All right, so implement this. I did. Note here that, again, we're eventually going to cover this more in depth. This is the next thing we're going to cover. But when you write a function, you in C, you put the documentation with the prototype. And then you don't repeat the documentation because of the DRY principle. Don't repeat yourself. Right? You write it once, you put it somewhere, and then that's it. Right? All right, so I've got that product. Oh, and again, we haven't covered functions yet, but let me go ahead and try to compile this. And with warnings on, so it can tell me what's wrong here. There we go. Warning, control reaches non-void function. without returning anything. We need to return the product. There we go. Because with functions, you give it input, it needs to give you output. So in the function, you have to say, what am I going to give back to the calling function? And here, it's the return statement here. I also need to bring in the math library, I think. There we go. We're all good. Let's run this and see if we're not printing out anything, right? So we need to go back up and fix it. All right, so once we've computed it, we're going to output it, printf. Right? Sign of %f, that's going to be x, is equal to %f and the line. Right? And that's going to be x and then the sum that we actually computed. Right? Also, what I want to do is output, say, sine of x. I want to compare them, right? I'm going to output my version of sine, and I'm going to output the official version of sine that is defined in the math library, and let's see if we're close. That's a great test, like an ad hoc test that I would run just to see as a sanity check here. Yeah. All right, so what's wrong? Or is there something wrong? Here, what do I want to say? 3.14159. Yeah, there's definitely something wrong here. It should be 0. It's never going to be, okay, yeah. Let's try 6 iterations here. GCC, run this. And yeah, okay, there's something wrong here. All right. Sine divided by factorial.
Is it the formatting?
Oh, is it? %f.
LF or
That's for reading it in. You can do LF here, but that's not necessary. It's definitely not integer truncation because I am getting a floating point number here. Let me make sure that I transcribed it correctly. So raised to the 2i, and it should be x, and x does not change. 2i plus 1, turn it. And it starts out as positive, right? Yeah. Let's go with, okay, so here's another way we can ad hoc test this. What if I went for 1 iteration, right? Because it's going to be 0, and then I is less than or equal to 0. What should we get out of this? X back, right? And so we are. Now, what if I go 1 iteration, right? Now, what we're going to do is we're going to go over here to Wolfram Alpha, and I'm going to get pi, which is pi, come on, plus, and then whatever the second one is. So let's figure this out. When I is 1, that's going to be negative on the top, and then 3 factorial. All right, so come on, pi plus negative divided by 3 factorial is 6, right? Plus negative 1 over 6 plus, x, which is pi raised to the power 3. So plus pi raised to the power 3. Right. Oh, sorry, that's not plus, that's times. There we go. So I should get negative 2 something something. It's going to oscillate, right? It started out large, pi, then it goes, jumps to the other side, negative. It's going to jump back and forth because it's oscillating, it's alternating. So let's go ahead and see if this works. Nope. All right, there's something definitely wrong that I'm not seeing here. X is pi, sine, sum, n. Darn it. So let's take this and put it into another variable. Oh, by the way, this is poor man's debugging, right? Because we can't afford a proper debugger yet, because we haven't learned it yet. So what I'm going to do is I'm going to put this into another variable here. Not int, but double y is equal to. Actually, now I'm thinking that there is integer truncation here somewhere. Yeah, Okay, I figured it out. Did you? The hint I'll give you is integer truncation. Well, what's an integer? Sign. What does factorial return? An integer. So in this right here, sign divided by this is why we never make progress away from pi, because we're always adding 0. So what can I do here? Double. Is there going to be a problem with pow over here? Nope, because that returns a double. GCC this, run this, and it should be, yeah, I'm getting that negative 2.02 that I computed over here in Wolfram Alpha, negative 2.02 and change. So now let's restore this up to, what, 5 is what we were trying? Right? GCC this, and it should be zeroing in on 0, right? Remember that it's not going to be exact because we're only doing 5 iterations. What if we did 8 iterations? Right? Run that. Right. It starts getting worse. All right, let's go ahead and go down to back to 7 iterations here. I wonder why. There we go. Okay, that's still worse than before with 5 iterations, but so why is that happening? Now put on your calcats and figure this out. Oh, actually, no, it wouldn't be your calcats that would tell you this, because what do your calcats tell you as far as the approximation of a Taylor series to sine? The more terms that you put, the more that it starts wrapping around, right? Initially, it's just a cubic equation, right? It's going like this, and it only approximates it around 0. But then you add another term, and then it starts, collapsing in on the sinusoidal curve here. And that's why if you do that infinitely, then it will converge and match exactly. But think about what's happening here when I do factorials. Right? By the time I get to 7 here, 7 times 2 plus 1, that's 15 factorial. Right? 15 factorial. How big is that? That's really big. Right? That's what? That's going to be 1.3 trillion. Remember that we only have 17 digits of accuracy. So at some point, these numbers become so big that the denominator becomes so big, the entire expression becomes so small. Now you start to have errors propagate. Right? So the takeaway here is, even though that this is a nice little exercise, is it the way to go about doing it? No. The Taylor series are very bad in computing. Right? So there's probably some other numerical interpolation, like a linear interpolation method or something. Right? All right, non-math? More math? More math? More math? No? All right, then suggest something. Like I said, we could do not biology, but chemistry? Physics, I guess? So what? No? No suggestions? The rate of decay of a radioactive isotope is given in terms of half-life, right? This is usually my go-to, and especially in CS2. So for example, strontium-90 is radioactive and has a half-life of about 30 years. So in other words, if you started out with 10 grams today of radioactive strontium, then in a year, you would only have 9.76 grams. Now it doesn't just evaporate, it decays into a product, into something, I don't know what it decays into, what is it? Did I say in here? Iridium, I think. Yeah, iridium and zirconium, right? Those are also radioactive isotopes. Those decay. Eventually, everything decays into a stable isotope, right? Eventually, right? Some things have billions of years as a half-life. But this table represents what happens over time, right? After 2 years, you would only have 9.53 grams left. ... After about 29 years, right, because the half-life is 28.9, you would have 4.99 grams. In other words, you have half as much as you had before. Okay? So let's go ahead and produce that table by reading in the following inputs. And I'm just going to hard code these. But I have an atomic number, which is an integer, an element name, an element symbol, a half-life, and then an initial mass in grams. And we have to produce this table. We know that from the half-life about how much we're going to do, but what I want to do is I want to look at the actual mass. I'll have 10 grams to start out with. I will update that to 9.76 grams, update that again to 9.53 grams. And once that gets below down to the half of the original mass, that's when I'll stop. Okay? All right, so I need an atomic number. Actually, we don't need much of that stuff. We just need a half-life and the initial mass there. Right? C or Java? Java? All right. And also, somebody had asked on a code post about their white space. You can see here that I've enabled it. It's kind of annoying, but you can see the difference here. That these are tabs, right? And it's actually showing you the white space tabs. And these are spaces because they're dots. And then I've got an n-line paragraph symbol right here. And so you can see that if instead of spaces I were to actually use a tab, you can see the difference. If you were to take this on another system where a tab here, it looks like it's 4 spaces, but on a different system, a tab might be 3 spaces or something, right? So just be consistent, right? All you have to do is hit Shift Command F and it'll reformat everything for you automatically. Right? By the way, how do you remove that stuff? I posted it on Code Post. I think it was a public post. But you can go up to Settings, Preferences. You can go search for text editors. Right, there we go. And then where it's so small, show white space characters right there. And I'll disable that right there. Right? And now we're back to normal. Right? All right, so let's go ahead and have an initial mass. Initial mass. And I'll set it equal to that 10 grams that we were talking about. By the way, just setting it equal to 10 there, does that tell you that it's in grams? What if I had another variable that was supposed to be in kilograms and I tried to add them together? Would they match? Nope. So you do have to be careful about units, basic units, when you're talking about programming languages like this. There are some languages that allow you to define natively to define this variable is in grams and this variable is in kilograms, so that when you add them together, it automatically multiplies this by 1,000 to give you kilograms back. Right? There are languages like that, or the things that you can do to define that. But generally, what you do in a language that doesn't support that is you would have another class that and we'll do this next semester. You'd have another class that represents mass, right? And then internally, it would keep track of what units it's in. So that if you had this mass and you tried to add them together, it would automatically, coerce them into the correct units to matching units. We're not going to go that far, though. Another thing that people do is they put it into the variable name. You can do that, but generally, it's not done. Right? You just should, know, fundamentally what you're working in here. And by the way, that has caused problems. I don't know if I mentioned it here, but there was a Mars rover. One system was in imperial, one system was metric. Right? Why that system was imperial? Idiocy. And ever since then, NASA has banned anything that has been in imperial, but they failed to convert between the two systems, and so the Mars Explorer just crashed right into the planet because it was going way faster than it should have. Right? Hundreds of millions of dollars down the drain. All right, so double initial mass. Right? And then we also want a half-life. Technically, I think that's hyphenated, but we'll just go ahead and go like this. Right? Because you cannot hyphenate variable names there, right? Half-life. All right, it was 28.9 years. Right? And again, do I know what the units are here? Well, this could be seconds, this could be days, this could be billions of years. I could put years in there, but again, that's kind of, it should be understood. Right? Okay. All right, help me to produce this table here. Now, here's a formula that we give. Right? After a certain number of years, y divided by the half-life. If you put that into the power of 1/2 times your initial mass, that's the amount of mass that you have left over. And it makes sense because why do we call it a half-life? Because it's half. After 1 year, right? Or if you went all the way to the end of the half-life and y is equal to h, then the exponent is now 1 and it becomes 1/2 as much as you originally had. But otherwise, 1 year divided by the half-life raised to the 1/2, that gives you the value there. So let me go ahead and create a variable called mass is equal to 1/2 times raised to the power, raised to the power y year divided by half-life. All right, well, first of all, is it wise to do integer division like that? That's immediately what? 0. So 0.5, and then this is all raised to this power. Okay? But I can't do that. Instead, what do I have to do? And in this case, it's math.pow, right? Because it's in the math library. Java, everything belongs to a class or is a class. Right? In this case, the pow function belongs to the math class. I don't have a year variable here. Right? Let me go ahead and create double mass is equal to. That's what I'm going to iterate on, right? Initially, the year is going to be 0. Right? And then 1, 2, 3, 4, all the way up to 29 here. So let me create that variable, int year, and it'll be 0 initially. Right? What happens to this this value here? 0 divided by half-life, that's going to be raised to the 0, and that's going to be what? Anything raised to the 0 is 1, right? And so 1 times the initial mass is the initial mass. Right? So I'm going to put this into a loop. Right? And printf, the year, which is going to be %d, and then I'll tab over, and then this will be %f, but I'll only go out to 2 decimal places here, and then I'll say grams, g, right? And then end line. And this will be the year and the mass. Right? Okay. Now that loop control structure, which one do you want to do? I know that I'm going to go for 28.9 years, but I'm actually not. I'm going to go whole years. So I'm going to go to 30. Right? So what you could do is you could take that half-life and then round it up, and you know exactly how many years you're going to go. Or remember that we just want to go until the mass has diminished to 1/2 of the original. So for loop or while loop? While? Okay. While the mass is greater than or equal to 0.5 of the original mass, right? Then I'll continue this. And this is system.out.printf. There. Now if I'm going to do that, I have to have this mass variable outside of this loop. So let me go ahead and create it up here. And I don't need to initialize it. I'll just go like that. And then I can't create it here. There. All right, now Java is complaining about this. C would not complain about this at all. That I never actually initialized this. So how can you check to see if it's greater than 0.5 the original mass? Huh? So what I'm going to do is I'm going to just set it to the original mass. Because the initial mass, the initial mass, right? That's going to be more than 1/2 of itself. All right. Let's run this again, or we haven't run it yet. All right. 0 and 1 gram. Okay. So, what happened? Oh, sorry, go ahead. The mass is missing. 10 is greater than 1/2 of 10. I don't think it's the while loop yet. But let's go. Here's a preview of something that we'll eventually do. I'm going to go ahead and set what's called a breakpoint. I'm going to show you these things early so that you know about them, because otherwise you'll be pulling your hair out thinking, I wish there was a better way of doing this. Remember I said that there was poor man's debugging where you can print stuff out, have a print statement. Here's the rich man's debugging, because we actually have a debugger here. If you just double click over here off to the side on any line, that'll set what's called a breakpoint. Instead of hitting the play button, you hit this little bug button. If you really look hard at it, it's a little bug. And that's the debugger. Let me go ahead and run it and change my perspective. I'm going to switch this perspective over to this over here. And that runs my program down to this breakpoint and then pauses it so that I can take a look around. All right? I can go ahead and highlight things. For example, the initial mass is 10. The mass is 10. Right? So I got into this while loop. All right? Now let's go ahead and step through line by line to see what we would expect. So go one more. There we go. And now the mass has been updated to 1. So I don't know what the problem is yet. I haven't figured that out. But I know where the problem is. That problem is on line 13. Okay? Because I'm not expecting 1 out of this. What am I expecting after the first year? 9.76. Okay? Well, take a look around at your other variables. Arguments were never defined. The initial mass never changes. That's still 10. You see it over here. It's being printed right here. Right? The half-life, that never changes. The mass changed, but it changed in the wrong way. So by process of elimination, what is the aberrant variable here? Year. Right? Did we ever change year? No. And where did we start the year? At 0. 0 divided by the half-life is going to be 0. Anything raised to the power of 0 is going to be 1, right? So I'll show you how to get out of this. Go ahead and stop it. We know what the problem is now. Go back to your Java perspective up here. It changed my perspective. See this little bug right here? Now there's a debugger perspective. I'm going to go ahead and go back to my Java perspective over here so I can fix it. Okay? Where should I have started my year? At 1? Okay. And don't forget, at the same time, what should I do with my year after I've computed everything? Year plus plus. Right? Go to year 2, go to year 3, etc. Run this. Ugh. Okay. Well, 0.98. All right. What's the issue? Yeah. Mass.pow. Oh, good. All right. Come back over here. What did I miss in my transcription over here? Yeah, that mass, the initial mass. All right. There we go. And multiply. Let's run it one more time. Now it's getting to look something more like this. 976, is that correct? 976, 953, all the way down to 499 in year 30, or 29, I guess. Right. There we go. But it's not exactly like this over here, right? Sometimes when you're writing loops, you have to have an exception, right? Either the first iteration is off or the last iteration is off. And in this case, the first iteration is off. So I could try to fold that into my loop control structure somehow, or I could just do it manually. Yeah?
I was going to say, I think number 3 was off by 100 as well.
Oh, number 3, 930, 931. Yeah. Wonder why. 909. Oh, and I don't have anything left for it. But the last one was 511, so we got back to it eventually. Probably because we're doing initial mass times this, and probably what I did to produce that output was I just kept multiplying the mass by 1/2, 1/2, 1/2, and I didn't bother with math.pow. So I just probably did it another way, and then it only introduced things that are off slightly. Okay. I mean, if we want to, we can go out to 3 decimal places and see. But that first line, though, I do want to take care of that first line. Right. Instead of printing out a year, I'm going to print out that hyphen indicating that it's just the start. And then instead of printing out the mass, I will print, I could, but I'll print out the initial mass. And now this is looking very, very much like that table. Oops, sorry. Sorry, yeah, I need to get rid of this year now because I'm now printing a hard-coded hyphen there. There. 10 grams, and year 3 was wrong. And yeah, I don't know why. I don't know why. I mean, this was written a hell of a long time ago. All right. And we don't have the rest of this stuff, but you can go ahead and make it look as pretty as you want. All right. So one more test case here, because I don't think we're going to be able to do anything else today. What's your favorite isotope? Yeah, what's your favorite isotope?
Uranium, yeah.
235 or 238?
Although that's going to be a very long list.
Do 235 half-life. 704 million years. So, how do I do? I could do that, but 1, 2, 3, 1, 2, 3, right. And this is just going to keep going, going, going. It eventually will get there, but that's why there is natural uranium-235 naturally occurring, because it has such a long half-life. There's no natural strontium-90 that's produced in nuclear fission. I mean, there would be if you were near the birth of a star or the death of a star or something like that. But then, within 1,000 years, it'd all be gone. So yeah, I'm not waiting for this. There we go. Would we be able to get? Yeah, this is representable, right? 704 million. That's fine. If you wanted to, you could change this stuff into, I don't know, big double. There we go, and bring that in. Big decimal, I think it is. Decimal. Right. Bring that in. Import that. There we go. And then you couldn't just assign this. What you'd have to do is have to go new big decimal of. And then you have to put this as a string, and then it would parse it out and create a new big decimal. Big decimal, and then there's also big integer. Foo, I'll say new big integer. And here, you can go ahead and mash your keyboard as much as you want. Right, remember that 2.147 billion is the limit. There is no limit to big integer. There is no limit to, like 17-digit limit to big decimal. So, like I said before, if you need big numbers or if you need very, very accurate numbers, then you need to bring in a library to do it. In Java, the library is big integer and big decimal. Right? You pay a huge price for that. Right? First of all, you can't just say +1 or something like that. Instead, you'd have to say foo is equal to foo dot add another big integer here, big integer dot 1. That one's so common that they actually just made it into a static variable there. So if you wanted to add 1 to whatever this number is, you could do it, but you have to call a function to do it. That means that it's going to create a new class or an instance, and it's all done in software. Right? Whereas a small d double, a big small I integer there, those are all done on the hardware, super, super fast, or on a GPU, even faster. Everything involving big integer and big decimal is now done in software, which is orders of magnitude slower. Right? So you only do that if you absolutely need to. Okay. All right. Any questions? No? All right, when we come back on Monday, we could do more exercises if you want. We'll take a vote. More exercises, or we move on to functions and methods. But you should know that for your first exam, which is in week 5, we've covered everything for that. Week 5 exam, your first exam covers basic I/O, basic variables, the basics, conditionals, and loops, and that's it. All right? You can write functions if you want to, but it's not going to be graded on. All right, I'll see you on Monday then.